Hi everyone. So today we're going to review the idea of work in physics. Alright, so we're going to use the symbol of capital W to represent work in equations. Alright, so work is just energy. But it's, in a sense, the process of transferring energy to or from a system because of external forces. Right, so if an external force is applied to our system, it can add or remove energy from our system. So external forces are forces that are interacting with our system that are not in our system. Whereas internal forces are forces that only act within our system and interact with objects in our system and not with the environment, not outside of our system. So actually internal forces, these internal forces are going to cancel out. Right? So technically speaking, the forces that can do work, but the work of one of these forces is going to cancel out with the Newton third law pair, the equal and opposite force caused by another internal force, and those works end up canceling. So let's kind of get into the formula here. So work, if we look at our formula sheet for the AP formula sheet, right? Remember, so here we have the work energy equation, where we have change in energy is equal to the work. So work is actually defined by the, so to speak, second part of this, these multiple equations. So work is the component of the external force that is parallel to the displacement multiplied by the displacement. Right? So this F is the magnitude of the component of the force parallel to the direction of displacement, and D is displacement of our system. Right, so if let's say our system is just an object sliding across the table. So our system is just the object, we'll say. So if our object is going from one point to another, it displaces a distance, d. And here in the situation I'm looking at, let's say it's in the rightward direction. Right? So its displacement is the distance it travels. Whereas the force that I'm plugging into this equation is going to be the component of the force parallel to this displacement value. So for example, if we're pulling on some sort of object at the upward rightward direction at some angle, let's say theta, with respect to the horizontal direction, right? So our object here is still displacing from here to here, right? From the left spot to the right spot, but I'm doing this displacement here. I'm analyzing a force that is acting along this force vector direction. Right? So that force is pulling the object along here. So it's the horizontal component that I'm worried about in this equation. Right? So the horizontal component here, if we do a little bit of trig, we see that it's the adjacent piece if we draw our trig triangle. And that adjacent piece is going to be F cosine theta. So we can simplify our formula, or let's not simplify. We can further, we could also write our formula as the force we're analyzing, so the force that's doing the work, times the displacement, multiplied by the cosine of the angle in between my force vector and my displacement vector. This we'll work through a couple of examples to kind of show and emphasize how this formula works. We do have a new unit going on here. So if we look at our units, we've got force, which is measured in newtons, multiplied by displacement, which is measured in meters, and multiplied by cosine theta, which does not have any units. So we've got newtons times meters. So since this quantity, energy, is used so frequently in physics, we develop a new unit for it, just because, physicists are lazy, right? So instead of writing Newton times meters everywhere, we define that 1 Newton times 1 meter is called 1 joule. So 1, and we're going to symbolize that with a capital J. You might be familiar with this unit from chemistry class, right? So joule is a famous chemist and physicist. So there is a unit of energy is named after him. Alright, so let's look at an example here and how we can calculate work. So we want to see the work done in pushing a crate. So we have a student pushing a heavy crate 3 meters along the floor at a constant speed. She pushes with a constant horizontal force of magnitude 70 newtons. How much work does Sarah do on the crate? All right, so the student has a name. I'm going to switch over so I can write on here. Nope, that did not do that right. All right, sorry about that. So same example, so kind of highlighting some important things here. So we know that the crate is pushed 3 meters. All right. We also know that we're moving at a constant speed. Pushes with a constant horizontal force. So we have a horizontal force, magnitude 70 newtons. And we want to calculate, why is that not changing colors? Did it change colors? How much work does Sarah do on the crate? So we want to know, calculate work that Sarah does on the crate. All right. So let me zoom in here so I have a little bit more room to write. So kind of dealing with things we know in this problem. All right, so, well, maybe we should draw the situation first. Of course, what am I thinking? All right, so here's the floor. Here's the crate. I'm going to assume that Sarah is pushing to the right. So over here is Sarah, and she's pushing to the right. So this is F push. All right. So based on this, I'm also going to assume that the crate is moving to the right. So listing what we know. All right. So from this problem, we're told that the distance that the crate goes is, 3 meters was it? Let me zoom out. Sorry for the zooming. I really don't want to. So yeah, 3 meters, constant speed, force of 70 newtons. All right. So going back in here. 3 meters is our displacement. Our pushing force, we're told, is 70 newtons, rightwards. And we're moving at a constant speed, so acceleration is 0. And we're trying to calculate the work that Sarah does on the crate. So this is the work of our pushing force. So it's the work that she does on the crate is that pushing force, that force we're analyzing. So here, we're not dealing with the total work done, not the work done by all the forces involved in this problem. We're just interested in the work done by the specific force of Sarah pushing. All right. So this is a question mark. Well, we know we can calculate work pretty straightforwardly, right? Because we know that work, let me erase that. We want the work of the push is going to be FD cosine theta. F here is the force of the push times the displacement times the cosine of the angle between these two vectors. Right, so F push, that's 70 newtons. Displacement is 3 meters. So we just need to figure out what to put in for our angle. Right, so looking here, so I always like to redraw my vectors. Right, so I know here it's kind of obvious, or hopefully it's pretty obvious what direction the angle's in, but I'm just going to be pedantic here and kind of show how to systematically look at the problem. Right, so we have two vectors involved here, the force vector and displacement vector. My pushing force is to the right, so I'm going to draw that here. So it's F push. And then drawing on the tail of that vector, so I put a dot here to represent the tail end. I'm also going to draw my displacement vector. My displacement vector here is also acting to the right, right? Because my box travels from its location to a rightward location. All right, so looking, since these angles, these vectors here are parallel with each other in the same direction, there we get a angle of 0. So my pushing force is going to be 70 newtons. Pushing force, my work done by pushing, excuse me, is 70 newtons times my 3 meters times the cosine of 0 degrees. All right, so cosine of 0, that's just 1, so that's pretty nice. So my answer here is 210, and we got newtons times meters. Well, a newton meter is a joule, so we have 210 joules. So we got a positive value. All right. Now I just want to talk about another situation we could have. Right? So let's assume instead of Sarah pushing, we'll have Sarah pulling. So here what's changed, right, is instead of push, we've got pull now. Let's assume it's still with 70 newtons. Right. So now our pulling force, though, is not in the rightward directions. It's in the leftward. We're still going to assume that the object's displacing to the right, but Sarah's pulling on it. Right? So now Sarah's pulling to the left, and our displacement here is still to the right. So what's changed is our angle. Our angle here is now 180 degrees rather than 0 degrees because they're anti-parallel to each other. So cosine of 180 degrees is -1. So when we plug in our formula, instead of cosine 0, we have cosine of 180, it becomes -1. So we get a negative 210 joules for the work done by the pulling. Right? And having that negative sign is fine. Right? That negative sign indicates that the quantity is just negative. It's below 0. So now let's look at a situation in which we have a suitcase. So a force at an angle. So I recommend you stop, try to solve the problem, and then come back and see if you get the same thing I did. Alright, so I'm going to solve this through pretty quickly because I want to get this video less than 15 minutes. Alright, so work done pulling a suitcase. So we have a strap inclined at 45 degrees. As going through an airport, the tension in the strap's 20 newtons. How much work does the tension do if the suitcase is pulled 100 meters at a constant speed? Alright, so we've got a suitcase pulled with a tension force at an angle. Alright, here's the floor, so I'm going to assume that our suitcase is moving rightwards as I'm pulling upwards and rightwards. We know that this angle here is 45 degrees. Alright, so in this problem, we're given angle, 45 degrees, so careful. I labeled this as theta. It's a little sloppy. It may not actually be the same angle we're dealing with in the problem. We'll just double check. A tension force is 20 newtons. We want to find the work done by tension. That's a question mark, and we're told that we displace 100 meters, and our acceleration is 0 because we're moving at a constant speed. Alright, so since we're solving the work done by tension, we take the force of tension, multiply by displacement, multiply times the cosine of the angle between the two vectors. We know the tension force is 20 newtons. We know displacement 100 meters. We just need to figure out the angle. Trivially, we might think it's 45 degrees, but let's just make sure our problem's not playing a trick on us. It is that 45 degrees. So if our object's displacing to the right, and our force vector is off upwards to the right, this angle here is the angle given in the problem. That is the 45 degree angle. Alright, so plug in our values. Tension 20 newtons. If I remember correctly, when we plug this in, we get something around 1414 joules. I am not boxing this as my angle or my answer, right? Because looking at this has 4 sig figs, and our problem here has arguably 1 or 2 sig figs. So I'm going to do 2 sig figs here. So 1400 joules. There's my answer. All right. So it's just important here to double check that the answer, the angle that you get, is the angle given in the problem. All right. So now the question is, what happens if we have multiple external forces going on? How do we compute work there? Well, luckily it's not that difficult. We just find the net work done, the total work done. So we find the work done by each individual force, add them together, and that gives us our net work. If our net work is positive, that means energy is added to our system. If it's negative, it's taken away. Now we can have situations in which there is, you can't read that, can you? There we go. That's better. I'm sorry about that. So we can have situations where a force, an external force, does no work. Right? So looking at our formula for the work energy theorem, we can have where the F is equal to 0, so there's no force. So that's kind of trivial. We can have displacement 0, so if our object doesn't move from one spot to another, then there's no work done by an external force. And we can also have where the angle is when cosine of theta is a value of 0. Cosine theta is a value of 0 at 90 degrees and 270 degrees. So basically, if the force we're analyzing is perpendicular to displacement, then we can have no work done. All right, so quick question, 30 seconds. So I want you to pause and think about this question and give me an answer and what you think. All right, so maybe your answer looks something along these lines, where you have one axis being force, one axis being displacement. My answer here is actually incorrect. I need to have force times cosine theta. You can have a variety of answers just as long as your y-axis and x-axis multiplied together become force times displacement times the cosine of theta. All right, done. Whew.